Myself, Dr. Tanushree Ghosh, Assistant Professor from Department of Chemical Engineering, HIT India. Today, my lecture is on material balance and energy balance computation. Topic is problem solving for purging operation. Let's discuss shortly about purging operation. First, I want to say that what is it? What is purging operation? Purging operation is that type of operation when a fraction of recycled stream is driven out, and obviously it is a process operation in which a fraction of recycled stream is bled off to remove the part of excess accumulated impurities built up inside the process unit due to recycling operation that may cause the process stop automatically. Now, when the recycling stream is mixed with the fresh feed, then what happens if there are any inert material or any impurities which are present in the final product, which is coming from fresh feed also, that is accumulated. And if it is chemical reaction unit, that means reactor is there, so the rate of reaction will be hampered due to the presence of that impurities or accumulated inert. So to avoid that difficulties, if purging operation is done, it will help to overcome that difficulties. So this is a block diagram of purging operation where it is shown that fresh feed is here entering, recycled stream is here coming, mixed and giving a test mixed feed. After processing unit, after leaving this processing unit, what stream is coming out? That is feed test. Part of this feed test is diverted at recycle stream initially, and another diverted part is feed double test, which is discussed already in my previous lecture, that is recycling operation. But here, a fraction of recycle stream is bled off to avoid the accumulation of inert material, to improve the operation. Now, what are the significances? Firstly, it is removing the impurity in the final field, basically in the inside the reactor, that is removing the impurity. It cannot it protect to develop the impurity or accumulation of inert material, and by doing this it can improve the reaction rate in the reactor. And what are the applications? Applications are simply when ammonia, few applications, so many applications are there, like giving ammonia synthesis from atmospheric nitrogen and hydrogen. Obviously, there methane, argon, this type of component can come from here, and if those elements or components are accumulated in the inside the reactor synthesis unit, then what can happen beyond their permissible limit? If those are developed, built up, then it can hamper the synthesis of ammonia. So to avoid that difficulties, the purging operation is here carried out. Few other applications are here: electrolyte refining for copper, electrolyte recycling of electrolyte, and the steam boiler in case of methanol synthesis. Purging operation is carried out. Now, next, discuss about problem on purging operation. Let's see first what is stated in this problem. Carbon monoxide and hydrogen react to give methanol. Carbon monoxide, 1 mole carbon monoxide plus 2 mole of hydrogen is giving 1 mole of methanol. This is obviously balanced chemical reaction, and the conversion of carbon monoxide entering the reactor is only 20%. Then 100% reaction is not occurring. Conversion of this reaction is 20%. A feed stream consisting of 33% carbon monoxide, 66.5% hydrogen and 0.5% methane is mixed with recycled stream and sent to a reactor. All these computations are here on mole basis. The methanol leaving the reactor is separated. Methane and keep its concentration in the recycled stream at 3%. A portion of recycled stream is blown off for 100 moles of fresh feed determined the following. Now here methanol, when it is from what are the questions here arised? That is, firstly, the moles of recycled stream, moles of part stream, the composition of part stream, and finally the moles of methanol produced. So these are the questions which are arised here from this problem. Now let's see the block diagram. Here two units are involved, reactor and separator. So firstly, we are observing what? That when fresh feed is entering, the notation for fresh feed is A, 100 mole. Carbon monoxide, the weight fraction of the mole fraction, all compositions are here given by mole percentage. So that's why mole fraction we can write here. XAF here is represented for carbon monoxide. A is carbon monoxide, B is hydrogen, and C is here taken or considered as methane. So XAF is the mole fraction for carbon monoxide in present in phase feed A, that is 0.32. For hydrogen, mole fraction is 0.665 and for methane it is 0.005 as given data as per given data in the problem. When it is mixed with recycled stream and into the reactor, it is giving methanol product, and due to the 20% conversion, few amount of carbon monoxide and hydrogen is already present in the product stream, and methane is totally inert, so total methane is present as it is entering into the fresh feed. Same amount of methane is present here. Now, when this methanol is separated from this unreacted carbon monoxide and hydrogen, and then from methane, we are getting two types of product. One is recycled part and another one is final product, where pure methanol is obtained. And the total moles of methanol, or that is total product stream, here A mole is considered, and the recycled stream, part of this recycled stream is part stream. Total moles of part stream here is assumed P mole, and recycled stream, the total moles of recycled stream here is considered R mole. The composition of recycled stream and part stream is same, obvious. So as per given data in the problem, methane is 3% present in part stream. Obviously, in recycled stream, same composition will be there, mole percentage. So that's why mole fraction of methane, where it is written X suffix here, that is 0.03, and in case of part stream, it is written XCP. It is wrongly written, XCP it will be, and XAP for carbon monoxide, and for hydrogen, it is 0. Now for methane, here as because 3 more % of methane, so that's why mole fraction is XCR equals to 0.03, we can write. And for carbon monoxide, we have to assume the mole fraction, that is X. If it is X, then we know 3% is methane, so rest 97% is totally carbon monoxide and hydrogen together. So obviously, if it is the mole fraction is X for carbon monoxide, for hydrogen it will be 0.97 minus X. And same composition are here reflected, that is for methane 0.03 mole fraction, and for carbon monoxide here XAR equals to, we are taking here X same as it is in present in part stream, and for hydrogen 0.97 minus X. Now firstly we are taking the basis to start the solution. Basis is here taken 100 mole fresh feed. If we do the material balance on this envelope, which is covering this reactor, this mixing point, separator, then we will find here the tie component is inert material, that is methane, which is entering as a single stream in a fresh feed and leaving as a single stream with the single stream part stream. So tie component is here obvious, the methane. If we do the tie component material balance on this envelope, if we do the material balance for tie component, that is inert C methane, we can write this F into XCR, F into XCF, sorry, equals to P into XCP. Okay, or 100 into, by putting the value of F, that is 100, and then XCF, it will be changed XCF here also XCP, XAP. Now, if we do the component material balance on this envelope, then we will see what F into XCF equals to P into XCP. By putting the value of known parameters, that is F, it is known 100, and XCF is obviously 0.005, and P value is unknown, P mole, which is to be evaluated here, P into 0.03. That is the mole fraction of methane in P stream. So finally we are getting what? P equals to 16.67 mole, which is the answer of B question actually. Next, if we do the carbon balance on this envelope, what we will get? Carbon means carbon is present in carbon monoxide, methane, and here in part stream there is carbon monoxide and methane also, and for product stream, that is here M mole. In M mole, there carbon is present. Now, by drawing this envelope, here actually total inlet stream is single inlet stream is here, fresh with A, and 2 outlet stream are present. That is total reactor and separator. Here, these two things and mixing point, all these things are coming under same single unit when we are drawing this envelope. So obviously, inlet stream will be here only fresh feed, and 2 outlet stream we are getting part stream and the product stream. So carbon balance when we are doing, then we can write what? 100 mole. In 100 mole, carbon monoxide is present how much? 100 into 0.33 plus 100 into 0.66, 100 into, for methane 0.005. So these are total number of moles of carbon monoxide and methane at inlet condition. Now at inlet point, whatever carbon monoxide, if in 1 mole of carbon monoxide, 1 mole of carbon present, in 1 mole of methane, there 1 mole of carbon is present. So obviously, if we do the carbon balance, same thing we can write as we are doing for carbon monoxide and methane. We can write here also for carbon balance 100 into 0.3, 100 into in bracket 0.33 plus 0.005. This is the total carbon in mole which is entered. Then total carbon which is leaving in mole, that will be coming from part stream and product stream. So in part stream we are getting what? P into methane, that is it is present P into 0.03. So out of this P into 0.03, again carbon is obtained P into 0.03. So simply if we do the material balance for methane and carbon, we can get also in the same mole, number of mole for carbon as we are getting for methane and carbon monoxide. So P into 0.0, P into in bracket 0.03 plus X, it is giving the total number of mole for methane and carbon monoxide present in P mole. So same number of mole for carbon will be obtained as it is written here. P into in bracket X plus 0.03 plus M, mole is total product. In number of mole, total number of moles is M mole. So in M mole, total number of methanol, that is M mole, and in 1 mole of methanol, we are getting 1 mole of carbon. So obviously, total number of carbon present in M mole methanol, we can write what? M into 1. Finally, we are getting what? If we write all these known value, if we put the total the known value, that is P equals to already evaluated 16.67. If we put that value, we will get this equation where M and X, these two only parameters are still unknown, which is given as equation number 1. Next, if we do hydrogen balance, then what we can write? Now let's see hydrogen balance, how it is coming on envelope, on this envelope. Hydrogen is present in hydrogen and in methane. Here is also hydrogen present here and in methane also. Here in product, in methanol, there hydrogen is present. So in hydrogen, in 1 mole hydrogen, we are getting 2 moles of hydrogen. In 1 mole methane, we are getting 4 mole of hydrogen. And here, 1 mole of methane, same is here. And for methane and hydrogen, 1 mole hydrogen it is giving elementary balance we are doing. So elementarily we are getting hydrogen 2 moles for 1 mole total hydrogen molecule, and from methane we are getting 4 hydrogen elementary. Elementary we can write 4 into 1. So here 2 into 1. If P mole is present, that means P into 0.03, that is the total number of mole of methane. In that P into 0.03 methane, how many hydrogen mole we are getting? On elemental basis, that is 4 into P into 0.03. From hydrogen, we are getting P into in bracket 0.97 minus X into again 2. So, thus we are getting total hydrogen from P mole. From product, we are getting, if 1 mole methanol is giving total hydrogen, total hydrogen 4 mole. That means in a mole of product, we are getting n into 4 total hydrogen elementary basis. So here we are doing say 100 into 2 into 0.665, that is coming from hydrogen, and 4 into 0.005, it is coming from methane. So it is coming at the left hand side, it is giving the total hydrogen elementary on the basis of element hydrogen. We are getting total number of hydrogen element, that is 100 into in bracket 2 into 0.665 plus 4 into 0.005. Again we are observing here 0.665 into 100 plus 0.006, 100 into 2 into 0.665 plus 4 into 0.005. Next, right hand side, P into in bracket this part and 4 into M, what I have already told. P into in bracket 4 into 0.03 plus here 2 into in bracket 0.97 minus X. This is from part stream, and from product stream 4 into 4 into M. So that's why it is written in this way. And finally, what equation is formed? That is, after putting this value P, we are getting 2M minus 60.67X equals to 50.33, where M and X are still unknown. Thus, equation 2 is developed, and solving these two equations 1 and 2, we are getting two unknown parameter M and X. So, from carbon balance, we are getting equation 1, and from hydrogen balance, we are getting equation 2. From these two equations, we are getting these two unknown values. We can evaluate these two unknown values, M and X. M is the total number of moles, that is the methanol, and X is the composition of carbon monoxide, which is present in part stream as well as in recycled stream. So, mole percentage, what you can write? If X is 0.3134, we can write 31.34%, and naturally hydrogen will be 0.97 minus X into 100 percentage, is giving 65.66%. So this is the M which is obtained, that is the total number of mole of methanol which is obtained or produced from this reaction, and X is giving the compositions. In terms of percentage, you can write it this way. So this is the part of answer C. Okay, next is methanol. If we do the methanol balance on the reactor, what we can write in general, by general statement, we can write here methanol entering was plus methanol produced, and methanol is produced by 20% conversion of carbon monoxide and hydrogen, and that equals to methanol what is leaving. So methanol what is entered in the block diagram, we have observed that no methanol is there entered before reactor. Only carbon monoxide, hydrogen and methane. In recycled stream, same components are here present. After reaction, only we are getting the methanol. So, and here 20% conversion is occurring. So, what we can write what? Methanol entering, that is 0. Methanol produced, what is that? 100 mole is feed. Out of 100 mole, their carbon monoxide is 33%, so 0.33 is the mole fraction of carbon monoxide, plus R, that is the recycled stream number of moles, into X, that is the carbon monoxide mole fraction. So R into X plus 0.33, that total into 100, it is actually, if it is 100% conversion, then we can write this one. But as because it is 20% conversion of the offer, that's why we are writing into 0.2. So 100 into in bracket 0.33 plus Rx into 0.2 is there. That's why it is written. And finally, it is giving total number of moles of methanol, that is N. So here R already obtained in the here. Here R we have to determine, only X is determined here from here. That is the answer of C. So by putting this value of X and N value already determined here 27.78 mole. So by putting these two X and N value, we will get this value of R. That is the total moles of recycled stream. That is R equals to 337.91 mole. This is the answer. That's all. Thank you.